All right. So thank you all for joining today's training session about heat transfer and air conditioning. So there are basic information about how to transfer heat, what are the physical principles, and about air conditioning, about the literature, and about some basic principle that will help us in our daily life and daily job with Continuum. So this session is recorded so we can review it after, and you will receive a full transcript of everything that was said, so you can refer to it. But please feel free to take notes, and especially don't hesitate to interrupt me. All right. So I would like to start by expressing my gratitude to Professor Ryuji Sakai, without who we will not have the pleasure to meet on a Sunday morning and doing what we are doing. So I wanted to start with this, just to express my gratitude to him and to the team composed of Matsuhashi-san and Claudio, who we are. So now, just for those who've never seen this slide, we are growing a network of distributor that I have the pleasure to organize in Asia, but also in Europe, in North America, and Africa and Middle East, and growing basically every day. So first, let's talk about heat transfer. So there are basically 3 different processes to transfer heat. Number 1 is conduction. So it transfers the heat from one molecule to one molecule, so through the matter. So you have matter that are very conductive, like some metals, okay, and matter that is not conductive or very poorly conductive, like air. Air is a matter, okay, whether it's a gas, a liquid, or a solid, you have matter, and the heat can be conveyed through the molecules from one to another one, and this is named conduction. You have another way to transfer heat is convection, which is a little bit more complex. It's due to the movement of the fluids exchanging the heat from the hot point to the cold point, and you have some movement because a fluid, hot fluid is lighter, like the hot air is lighter and will go up, and the cool air is heavier and will go down. And these generates movement and generate heat transfer by convection. The third one is named radiation. So this is radiation is emission by electromagnetic waves, basically. If you are in a room, okay, where the air, if you take a temperature, a thermometer, the air is, let's say, 25, okay. But if the walls around you are, let's say, 0 degrees Celsius, you will feel cold. Even though the temperature is 25 degrees in the room, you will feel cold. At the opposite, if the walls are, let's say, 40 degrees, you will feel hot, even though the temperature inside the room is 25 degrees Celsius. The reason for that is the irradiation, okay? So it's another way of heat transfer. And one is missing, and it's a bit more complex, but I believe it's also a way to explain how Continuum helps to reduce energy consumption, is the vaporization. The vaporization, when you spray some water on a very hot surface, if you spray like very fine particles of water, like brumization, the vaporization, the transformation from the liquid water to the gas water will absorb energy. It needs heat, so it absorbs energy. So basically, if you have an outdoor terrace that is very hot, okay, if the floor is very hot and you spray a lot of water, you will absorb less heat than if you just spray some vapor of water, some very fine particles of water, because they will quickly evaporate, and the evaporation will absorb the heat from the floor. So that's another way to transfer the heat, okay? But the main three are conduction, convection, and radiation. Any question? Don't hesitate to ask questions. So this is a written way to say what I was saying. Conduction is the transfer of heat through the material due to a temperature gradient. The temperature gradient means you have one side that is hot and one side that is cooler, different temperature. It occurs when heat energy is transferred from one molecule to another within a material or between two materials in contact. This is very important. The conduction happens when you have two materials in contact, okay? I was explaining the water on the outdoor floor. The floor is very hot, the water is cold. You have a heat transfer by conduction. The contact between two materials makes conduction transfer, okay? Metals are good conductor of heat due to their high thermal conductivity. So thermal conductivity is just a measurement of how good the matter is to conduct the heat, okay? While what we call insulator, like air or some plastic, are very poor conductor of heat. They are insulating, they do not transfer the heat easily. Okay, and this we have in air conditioning, we have this phenomenon between the fluid and the coil, between the water and the coil. Okay, the fluid is inside the coil, the water is inside the coil, so we have the heat transfer. Okay, the water from the chiller transfer the heat from the coil, the metallic part, from the inside, and same for the refrigerant fluid, and also from the air and everything that composes the air and the coil on the outside of the coil. Okay, so you have the coil is a place what we call a heat exchanger, basically, because you have two heat exchange, actually. You have the heat exchange from the fluid that is inside the coil, be it water or be it refrigerant fluid, and the heat exchange between what is outside the coil and the coil itself. So you have the metallic coil, because the coil is metallic, is a place where you have a lot of heat transfer from outside of the coil and transfer from outside to inside of the coil, okay? Convection. So convection is the transfer of heat through the movement of a fluid, such as air or water. It occurs when a temperature gradient that I just explained causes a fluid to circulate, what I just explained before, carrying heat with it. Convection can be a natural or forced. Natural convection occurs when buoyancy forces and does not require external energy input. So it's kind of natural process, as I explained, with the different mass of the gas. The hot air goes up and the cold air goes down. And you can force this kind of convection. So that's what exactly happened in the room. So this is a phenomenon when we work on air conditioning, we see every time, because the air conditioning cools the rooms and we have this movement of air in the room. So it's always good to have these ideas in mind when we visit things, because if you get familiar to this phenomenon, you will see things differently, because if you are aware of that, you can imagine the movement of air and you can imagine what is well designed in the room or what is wrong in the room or what can happen, and that can have an impact on the functioning of the air conditioning, okay? And last is radiation, which is the transfer of the heat through the emission and absorption of electromagnetic waves. Unlike conduction and convection, the radiation can occur even in the absence of material medium, such as vacuum, in a vacuum. All objects emit absorb radiation with the rate of emission and absorption depending on the temperature and the surface property of the object. So basically, this is also something that we are working with, because the net, continuum net, emits far infrared rays. So this is a radiation, but not only the net, the walls, the windows, all these are emission of radiation. And all of these phenomena happens all simultaneously. All right. Any question on this? No? Okay. So we have to go a little bit more in detail in thermal conductivity. So thermal conductivity is, as I explained, is a measure of the material ability to conduct the heat. Okay. It is defined as the amount of heat that can pass through a unit area of the material in a unit of time. That's the way we measure how the material can carry and convey the heat easily or not. So you select one slice of the material, one area, okay? And you measure the heat transfer in an amount of time. So you have an amount of area and an amount of time, which is interesting. I will explain you why later. Under stable temperature difference. So this is how we measure the coefficient K of thermal conductivity, okay? And you have material with high thermal conductivity that are good conductor of heat, meaning that they transfer the heat quickly and efficiently, okay? Example of this material can be copper, aluminum, silver, basically metal, okay? And graphite and diamond as well, but we don't use very frequently in the air conditioning, all right? And at the opposite side, you have materials that are very low, that have very low thermal conductivity and are poor conductor of heat, that we often use for their property of insulators. And these can be fiberglass, air, and plastics, okay? So here you have example on the table. On this table, you have some examples about the thermal conductivity K for different materials. So you have from the best, silver, copper is one of the best as well, gold, and then you go back, you have glass. Glass is not conducting very well, and the heat, water, wood is a good insulator. Basically, you see the lower the number of K, the K number is, the lower is the conductivity. Okay, and air is the best insulator material because the K, the thermal conductivity is 0.024. Okay, the unit is watt per meter Kelvin. Kelvin is a measure of temperature, meter is a measure of length, and watt is a measure of energy. So this is expressed in energy per meter per Kelvin, right? The thermal conductivity, if we zoom into a air conditioning system, the thermal conductivity of refrigerant fluid can vary depending on the specific type of refrigerant used, okay? However, most refrigerants used in air conditioning and refrigeration system have relatively high thermal conductivity compared to other common fluids. So they use in the air conditioning and cooling system these what we call refrigerant fluids because of their proportionally high thermal conductivity. That means that they convey the heat in an easier manner. That's what we are looking for in air conditioning to be efficient, okay? So these are some examples. You don't need to remember everything by heart, but it's just to give you an insight and a culture of what is happening in air conditioning. So for example, R410A, which is one of the refrigerant fluid that is commonly used in air conditioning, has a thermal conductivity of about 0.085 watt per meter Kelvin at a fixed temperature of 25 degrees Celsius, okay? And if you compare with the thermal conductivity of the air, so it's not very high, it's much lower compared to copper, for example, if you remember the number that were very high, but it's still much higher than air, because air, the thermal conductivity of air is 0.026 compared to 0.085 for the refrigerant fluid, okay? So we convey the heat still about more than 3 times more with a refrigerant fluid than with air. That's why we use it, okay? And it is the higher is the thermal conductivity, the higher is the efficiency, because you can convey the heat, you can transfer the heat much faster. That's what is measured with the thermal conductivity K, okay? And something interesting also is that water, the thermal conductivity of water is 25 times higher than air, okay? Remember that. I will come back to this later.
I have a question.
Yes, Jenny?
So, for example, you said the most common types of refrigerant fluids are this R410A and R134A, and the conductivity is 0.087. So if somebody, for example, in terms of, you said the efficiency of conducting heat, et cetera, is like this number, which is watt per some MK.
Yeah.
So if somebody were to say, hey, like, or like somebody is selling refrigerant, let's say this new refrigerant that is more efficient than this number, 0.087, that would mean, let's say the number, like somebody invented a new refrigerant and instead of 0.087, it's 0.2 or something. I don't even know if that exists, or, you know, whatever, as an example. Yeah. So then that would mean their air conditioner is more efficient than this common R410, for example, A, right? Or not?
Exactly, correct.
Okay. So like, for example, the reason I'm asking is because a potential competitor sort of product would say, if somebody invented a more efficient refrigerant, to say, hey, by using this new refrigerant, your air conditioning would be more efficient.
That's correct.
By, let's say, 20% or whatever, you know, I don't even know if that exists, but I'm just saying that could be like a competitor product, right? Potentially.
So it's a very, very interesting question. Thank you very much for asking it. You open a very nice subject. Actually, these exist, okay? There are new refrigerants, because something that I did not develop here is that the refrigerants are very, very harmful greenhouse gas, okay?
Yes, yeah,
So
I understand that,
when there is a leakage, basically, these refrigerants, they go in the atmosphere and they are even...
And then create ozone, holes in the ozone.
Yeah, they have a destroying potential more than CO2. So they are very reflective of the UV light. So it keeps the heat more on the planet. So this is a problem, and they develop like greener, I don't like to say green, but greener refrigerant that are less harmful and that also have a better thermal conductivity. And they propose it to some company, but first, not all the air conditioning, you cannot mix and just remove the old refrigerant and put the new one, because the compressor has some setup. The way of functioning of the compressor, the way of functioning of the expansion valve in the air conditioning are designed for a specific refrigerant in general. It's like if your car, you use gasoline, you cannot put diesel inside because you will not go very far, okay? It's exactly the same principle. So not all air conditioning, you can change the refrigerant fluid that is there. So it's not, yes, it does higher conductivity refrigerants are doing the same thing as what we do with continuum. That means saving energy, not in such big proportion, I would say, okay? And I don't see them as at a competition, because even if you change, let's say it's easy to define very harmless new refrigerant fluid that has very high thermal conductivity, that is not bad for the environment, okay, and that can adapt to any air conditioning, the ideal case, okay? Someone created it. You change into the air conditioning, okay? Does not matter if you use continuum, you will still make the same savings because we are not working inside of the machine. You remember what I said? The evaporator coil, you have two heat transfer. One is from the air to the coil, the outer part of the coil, and the second one is from the coil to what is inside the coil, the refrigerant fluid or the water. So you can work to improve what is happening inside the coil. We work on what is happening outside of the coil, basically. So you can accumulate the savings. Did I answer your question?
Yes, thank you.
Thank you for asking. That was very interesting. Any other question on the thermal conductivity? Okay, I move. So yeah, basically as a summary, as you can see here, when we look at what is happening outside of a coil with air, thanks to the thermal conductivity, we can say that one particle of air, one area of air, okay, the heat transfer is small. That's what I could design with this small arrow heat. Heat transfer is small when you transfer the heat from air, but when you use water, okay, with the same coil, the heat transfer is bigger because of the thermal conductivity that is 25 times bigger into the water than into the air. And remember, we have water in the air, right? We have moisture. So basically, the biggest energy that we have to that an aircon has to remove is from the water, because it's the water that conveys the heat the more, 25 more than the air. If you have only air, dry air, there's not so much heat to transfer. Air is an insulator, right? So that's how also we have a very powerful tool with a continuum, because basically we know what we are doing with the water molecule, not only in improving the heat exchange ratio and the phenomenon we know, but also because we work with the moisture that is basically the item in the air that conveys the more heat, okay? So we have to talk a little bit about the evaporator coil. What is an evaporator coil? So an evaporator coil is in the air conditioning made in general of copper or aluminum or any kind of metal that are chosen for the property of being good thermal conductivity, okay? And this is very important device in the air conditioning because this is where all the heat transfer happens. The heat transfer from the air plus humidity to the coil, and the coil to the refrigerant fluid or the water from the chiller, okay? Everything that I'm saying, you can have hot air and you cool it with air conditioning, or cold air and you heat it with your heat pump. It's exactly the same phenomenon, exactly the same material. You can use the same material with some specific device, but for heating or for cooling, they are exactly the same phenomenon that is happening, okay? And the evaporator coil is designed to have the biggest surface area, okay? And the very thinnest possible wall to transfer the heat, basically, much faster, okay? And you have multiple options. You have multiple colors. Some look gray, some look black, some look like silver, some look blue, okay? But they are all the same. What makes the difference is the different treatment that these coil have. They have treatment to prevent from corrosion, treatment to prevent from the dust to be stuck in. But if you see a coil, you know what it is now, and you know that whatever is the color, it has exactly the same objective to transfer the heat.
Thomas,
Yes.
sorry, I've got a quick question. Just now you mentioned that it's the same process with a heat pump. And
Yep.
I know that in Europe, a lot of, especially, I don't know, in the UK, a lot of people are putting these new heat pumps in for temperature control in their house. So is that right, that they can use it in this new technology, the heat pump technology? They could use continuum?
So heat pump is I mean, an air conditioning is a heat pump. They are just two different words for the same thing.
Okay.
Heat pump is really a process word. Let's say you pump the heat. When you use air conditioning, you pump the heat from inside and you take the heat out, you pump it out to outside of your room, right? That's why you have cold air in the air conditioning. And if you go to the compressor, you have hot air because you pump the heat from inside to outside. In the opposite, in winter in Europe, they use heat pump. So they take the heat from outside, even if it's cold, and they put it inside. So it's a heat pump in one way or another. And the air conditioning in Europe in general works both way. You can select the heating mode or cooling mode. Now, heat pump is the process part. So you take the heat from one part of the building to the other part, inside, outside, or outside, inside. Okay. We can use continuum in heat pump, sure, when we are cooling or heating air inside. Okay. An air conditioning, as we know it, we are cooling the air. In Europe, sometimes they use exactly the same phenomenon. Instead of putting the coil into the air, you put the coil into a tank of water, okay? And you make the water circulate through some pipes in the floor. So you can cool the water or heat the water, whatever, and cool the floor or heat the floor in your house. This is a heat pump too. But you have the coil that is, instead of being in the air conditioning and blow air through it to transfer the heat with air, you transfer the heat with water. In this case, we cannot use continuum. This is also a very interesting question because I have it very often. And yes, heat pump we can use, but it has to be an air heat pump. What we do inside where we pump the heat or where we bring the heat must be air, because continuum works with air. I mean, the continuum net at least. Okay, did I answer your question? Is it clear?
Yes.
I guess, yeah, okay, thank you. So a bit of engineering. I did that because it explained a lot actually about continuum, okay? I would love to show that to our clients, but I'm not sure they will follow a lot. So it's about the Fourier's law of conduction. It's basically a measurement of the heat transfer and how do we measure it. So we were talking about the coefficient of the thermal coefficient K, okay? And here, so we have the example of a material which one side has a temperature T1, okay, a hot side, and the other side has a temperature T2 that is lower, a cold side, okay? The heat is not a vision of our spirit, is really something that we can measure, quantify. It's an amount of energy, is a thermal energy, okay, that we name Q, okay, that we can measure in joule, in BTU, in watt hour, in calories. This is real energy that you can measure and quantify, okay? And the heat always moves from the hot part to the cold part, okay? And as you remember, the conduction is in a material, okay? This, for example, can be the wall of the house. The outdoor part of the wall is hot, okay? If you measure the surface of the wall, it's hot. Outside and inside the house, if you have air conditioning, it's cold. So this can be a brick of wall or a wall of concrete, okay? And you have the heat transfer, and you can calculate, depending on the temperature outside, inside, on the thermal conductivity, K of the material, and on the surface, the area of your wall, how much heat is going from outside of your house to inside of your house, depending through the wall, basically. Depending on the thickness of the wall, depending on the coefficient K of the wall, you have the heat coming inside your room, okay? And this, I took the example of what is happening in the coil, actually. On the coil of the air conditioning, the evaporator coil. So we have on one side the air plus humidity, okay? That is hot, if we use in air conditioning, okay? And inside of the coil, we have the refrigerant fluid, okay? Or the water from the chiller. So we are really zooming into what is happening in the coil, okay? From outside the coil to inside the coil. So let's say we use copper. So we have a very good thermal conductivity K, okay? So the heat for one section, okay, is transferred from the air and the water. We know more from the water because the coefficient K is different, to the inside part of the copper of the coil. That will then transfer to the water. Here we'll transfer the heat to the water or to the refrigerant fluid, okay? So the heat here is transferred from the water, the moisture in the air and the air, goes through the metallic, the copper fin of the coil, okay? And then transfer again to the refrigerant fluid. What is interesting is not to know about all the details of the calculation, but something that is important for us to explain what's happening in continuum is we have to know that is the heat transfer. That means the speed with which we transfer is rely on the thermal, is proportional to the thermal conductivity, the contact area. This is very important, the contact area, okay, and the temperature difference, okay? That's what you can see here in this calculation. That's what we call the Fourier's law, okay? So this says that the thermal energy, the heat transfer, is proportional to the factor K, okay? The thermal conductivity, the contact area, A, okay? The temperature difference, okay? So the higher this number are, the faster you transfer the heat. And it's reversely proportional to the thickness of the material, okay? So you can imagine here in this example here, you can see that if the distance is smaller, you transfer faster, of course. If the distance is big, if you have a very thick wall, if you have a wall of your house, for example, that is like 1 meter wide, it will take more time for the heat to come inside your home than it is if it is just like a 10 centimeter wide brick wall. So that is all simple things that are expressed with the Fourier's law, but it's good to have it in mind that it is proportional specifically of the thermal conductivity, which is good because we are working with water, with continuum, and the contact area, which is good because we increase the contact area. So basically, we use the physical principles that are the most efficient to improve efficiency of the heat transfer from the air, okay? The temperature difference, well, so far we cannot manage how hot it is outside, so we are just coping with that. Okay. So this is a very simple way to show what I just explained. I think you know part of these images. So this is a big cluster of water molecule here. All right. When this big cluster come here, touch the fin, okay, of the coil, right here. So you have the big cluster. So the contact area is very small. So you have a very small heat transfer, right? But if you have the same volume with a lot of small water molecule, you have a much bigger contact area because all of these molecules will touch the fin. So if you increase the contact area, you increase the heat transfer by the law of Fourier, okay? So this is really scientific based. It's not new. Law of Fourier dates back centuries, okay? And that is exactly what we explain in a simple way to our client to show what is happening in continuum, okay? Now, about heat transfer, do you have any question? Because now we are going to move to air conditioning technology. No? Okay. So you became already expert in heat transfer. Wonderful. Morgan, any question? No? Okay.
No, it's fine. I love it. My connection is not that good, so
Okay.
I turn off my video, but clear, very interesting.
All right. Thank you. Okay, so now we are talking more about air conditioning itself. So what we talked before is what basically does an air conditioning or a heat pump. Okay, I call it air conditioning because here in our area in Asia, in Southeast Asia, it's more air conditioning than heat pump, but it's exactly the same. In the US, where Jenny is, they might call it more heat pump, but basically they're all the same thing. But now we are talking about general knowledge of what we have to know about air conditioning. Because we are not all technicians, not all engineers, but we basically every time we have when we talk with the decision maker on how on the people who want to save costs, when it's start to talk about technique, they put us in the hand of the engineers, and the engineers they talk with engineering words. So that's why we have to just know a little bit about the terminology and different units and how it works just in the basics. So the cooling capacity, this is very important thing of an air conditioning, and it refers to its ability to remove the heat from a space and lower its temperature, okay? It is typically measured in units of energy, such as BTU. BTU means British Thermal Units. I think Simon is very well aware of that since he's British, right? Or ton of refrigeration. So we have different words to different units to quantify measure of energy. So remember, cooling capacity, it refers to the ability to the machine to remove the heat from a space and lower its temperature. The air conditioning system work by using refrigeration cycle. We will go more in detail on that, to extract the heat from the indoor air and transfer it to outdoor environment. That is the heat pump. Like you imagine a pump that removes the water from your pool to put it out. You have the heat pump that removes the heat to put it out. That's exactly what it says, what I wrote here. So if you remove the heat, you have less heat inside, so the temperature goes down. Basically, we have to, this is important actually more than it looks, but it is very important to understand that we are removing the heat. We are not bringing cold thing, okay? There is no cold energy. I mean, basically, the energy, the heat is hot, and we remove the heat. The air conditioning actually doesn't blow cold air. It removes the heat from the air that is getting into the air conditioning, right? With all the principle I explained before. This is also sometimes important to remember, because in our daily life, we don't think about that when we meet the client, but when we think about this, then you understand a lot about the environment of a place. The cooling capacity of an air conditioning system is determined by the rate, basically the speed at which it can remove the heat from the air and lower the temperature to achieve the temperature setup, basically. The cooling capacity depends on various factors, including the size of the system. If you have a very small coil, okay, it will take time to remove the heat of a big volume of air, okay? If you have a very big coil, it will be faster to remove the heat from the room, okay? So this is one aspect, the size of the system, the efficiency of the compressor, okay, and the type of refrigerant fluid used, okay? So the type of refrigerant fluid used, we discussed with the question of Jenny, okay? and the type of compressor. We will discuss about it later because you have different technology of compressor that are more or less efficient. Okay. And basically, it also depends for where am I? Sorry. So it is important parameter also to consider when selecting an air conditioning system for a particular space, as undersized system may struggle to cool the space adequately and result in increased energy consumption, when oversized system may result in inefficient operation. So when you have a space to cool, it is always, and this is what we do every time before we start a proof of concept. I think the next training I will do it on proof of concept, how to do it and what we have to look at, because we discussed about that with the Vietnamese team, but I will do a proper training like this in the future. But it is important to check that the cooling capacity, okay, is well sized. The size is good for the space. The space means how big is the space, the volume of the space, how many heat you have to remove. Like, just think of a water pump, okay? If you have a swimming pool, you want to empty it, you take a very small pump. The small will burn, the pump will burn because it's too small. There is too much water to remove, and it will take ages, and you will never empty the pool. And the small water pump will run 100%, which will increase the power consumption. Now, if you have a very, very big pump for a bucket of water, okay, it will not be very efficient either, because there is so much extraction that the pump don't need to operate at the normal speed. So this is very important. It's easier for us to conceptualize the water pump than the air pump, the heat pump, but they are exactly the same principle. So we have to be careful about the size being not too big, undersized, or not to be too big, oversized. And the cooling capacity of an air conditioning system is important parameter to consider when you choose an air conditioning that is suitable for the cooling needs of the particular. So this is the heat load in the room, okay? Any question on that?
Yes, I have a question.
Yeah.
So basically, when we start talking to clients, and correct me if I'm wrong, we have to make sure that their air conditioning or heat pump or whatever there is that they're using is, first of all, a heat pump or air conditioning always for air, right? Generally speaking, air conditioning is always air, and then heat pump, sometimes you said it's potentially could be a water heat pump. But
Yeah.
for a water heat pump, we can't use continuum. So we
Yeah.
have to make sure if it is a heat pump, it's an air heat pump. But also we have to make sure that the capacity of this air conditioning or heat pump is sufficient enough for whether it's like a factory or whatever is sufficient enough. Because if it's not sufficient enough in terms of the BTU for the space, then continuum is not going to work.
It's
Correct.
not that it's not going to work. Continuum will always work, but the result will be different.
Right.
So first, there are multiple aspects about heat pump. Yes, correct. We have to work only with air heat pump. I don't know in the US if they use a lot the word heat pump.
I think it's starting to be used
Okay.
because the US Department of Energy started to have this new platform that they're trying to get consumers to look at other energy efficient options or how to save energy. And they said changing to a heat pump is one of the efficient tools. I don't know what it would have been before. Maybe they were, instead of a heat pump, I think maybe they're burning oil. I don't know. I'm not an engineer. So, I don't know if people were burning oil and then maybe had a radiator, or I don't know what the other option was instead of having this heat pump. So there's this sort of trend, I would say, to try to get people to switch over to a heat pump. I'm not sure if this switch over to a heat pump is a water heat pump or air heat pump. I'm not sure.
Well, I mean, they can do both. Basically, it's easier to switch to. It depends on what they had before. Basically, if they were heating, if we take a house, okay,
Right.
if they had a boiler to boil water and circulate water in the floor through pipes, okay?
Mhm.
They can use a heat pump to heat the water and heat inside, okay? So that is a heat pump. You have the coil, but the coil is in the water, so we cannot.
Right.
You use the
Okay.
same. The British has this because I spent some years in Bristol in the UK. They use a lot boiler, but they heat the air. Okay, so they have they don't call air conditioning or heat pump. So they have some kind of boiler, gas burner that heat the air and they blow the air inside. They will probably now switch to heat pump that is more efficient. Okay, I will come to that. Why we do that? Because we use less energy, okay? So they will use the heat pump to heat the air. So the coil will be in the air, so we can use continuum. So they are the same machine, instead that the coil is in the air or the coil is in the water. So they are both heat pump. Something that if they use HVAC system, HVAC is also another term to say air conditioning, reversible air conditioning.
Yeah, it's heating,
Heating,
yeah,
ventilation, and air
ventilation, air
conditioning.
conditioning.
So this is really, if you have a HVAC, it can be only with air, so we can use anyway,
Okay.
okay?
But and so yeah, Thomas, sorry,
Yeah.
so to bring it back to what we do when we arrive on a site, we could have, and it's maybe something to provide to the network, an easy formula to say quickly, okay, within a minute or less, is the cooling capacity good enough or not? Like it's what we do when we arrive in a space. We ask the owner the square meters. Okay, you have 250 square meters, 5 air conditioning of 40,000 BTU, and then quickly, okay, 40,000 by 5 machine, 200,000 BTU for 250 square meters, and just being able to, within a very short period, even if we don't say that to the owner, but immediately we have that calculation in mind, and we know briefly if it's if the cooling capacity is already good, so it gives us good information on the efficiency of continuum.
Yeah, no, it's a very good remark. I wrote it down. I have to work on some guidance because I mean, it must be a simple guidance, but that will not be 100% reliable because sometimes there are things that we don't see. It is always very important. That's what we do, and I will write some guidance to everyone to do exactly what Morgan just said, to check the volume of the space, estimate how much heat there is inside, and say, okay, is this cooling capacity good enough or not? Okay, this is very important. It's not always easy because sometimes you are in a small area, in a small. I'm thinking about a test we did at one factory where we were in a separated building, but the building was just like a small house made of bricks, a lot of windows, single layer windows, and a metallic roof under the sun. Okay, a lot of heat, a lot of heat. So if this room, the same room, was inside the building, in the middle of the floor, with the same air conditioning, the cooling capacity would be good enough. But since it's outside, I can tell you that between 11 a.m. and 6 p.m., the air conditioning was not sufficient. The cooling capacity was not sufficient to cool the space. And in this case, actually, yes, continuum cannot cope with this because you have to get enough cooling capacity in order to improve, in order to save energy. On the other side, if it is just a little bit undersized, like we did with Anantara in Boput, that's what we checked. So they had in the same similar kind of room, but they had a good cooling capacity for 25 degrees Celsius for the set point, okay? Right? And we saved, just make it simple, something like 30% when we did the test for 25 degrees Celsius set point of the air conditioning inside, okay? And then after they did another one at 23 degrees Celsius, so they decreased by 2 degrees Celsius the temperature, okay? and decreasing by 2 degrees Celsius, you have more heat to remove, okay? And the air conditioning became too small in terms of capacity. And therefore, when we make the baseline and measure the consumption in normal condition, the power consumption increased a lot. And when we input continuum, since it was just a little bit undersized, we just started to do refrigerant cycle that we are talking here again. And then the saving was very big. So we switched from 30% to 40%, right? But if it is too big of an undersized cooling capacity, then we can cool better, but we cannot save energy. So that's why the cooling capacity is always very important to estimate. But I will work on a specific guidance on that. And because, yeah, it is important. But this would be only a guidance. What I am afraid of is that just because it's written on a slide, it's always working. No, we have to always look around. And if you have, for example, let's take a supermarket, you have a good cooling capacity. Okay, you look and say, oh yeah, good. We have 5 air conditioning, 60,000 BTU. It's 300,000 BTU. The size is good. Okay, perfect. But if you don't check that they don't operate all of them at the same time always, that will not make it also. If you don't check that maybe one of the air conditioning, the maintenance is poor and they don't work efficiently, that will not bring the good cooling capacity as well. So it's not there is a theoretical guidance, and then after there is some engineering work to check that everything is functioning well in terms of operation. But I will try to drive the guidance. Yeah, you're right, Morgan. Any other question?
Maybe it's a checklist with checklist with different points, and at least it gives already some information. And after, as you said, it is very important. We see that every day that we have to customize building per building.
Okay. So we were talking about the efficiency and why we were moving from a gas burner or oil burner to heat or water, something like that, to a heat pump or air conditioning. Because we have a coefficient of performance, or EER, energy efficiency ratio. So there are 2 ratios that measure similar things in just slightly different way. That is very effective. So the COP, coefficient of performance, is a measure that is used to evaluate the efficiency of a heating or cooling system, including air conditioning system. The coefficient of performance is a ratio that quantifies the amount of useful heat removed or provided by a system in relation with the amount of energy input required to operate the system. What it means, okay, it's a very simple way, actually. It's a very simple thing, actually. It means that the COP make the balance and tells you how much energy your system is using. So the power in general, air conditioning, we plug to the electricity, how much electrical energy you use, okay? And how much energy, heat you remove or you bring into the room if you are heating, okay? And if with energy, you can compare energy. You can compare kilowatt hour and kilowatt hour, okay? Whether they are electrical energy or heat energy, you can measure in the same units, okay? If your electrical energy is smaller that you consume, that you pay for, is smaller than the heat energy that you remove, the coefficient of performance will be high, okay? Because the smallest energy you use to remove the higher energy, the thermal energy you remove, that's better. So the higher the COP, the better, okay? In the context of cooling, the COP represents the ratio of the amount of cooling capacity provided by the system in BTU or in watts, what I was just mentioning, to the amount of energy input required to achieve that cooling in BTUs or in watts. However, for cooling system only, a different term is called energy efficiency ratio. Okay, so they measure basically for air conditioning only, not in heating, but only in cooling. Okay, it's very similar to the cup. It's just expressed in a slightly different way. I will show you in the next slide. So as I was explaining, the higher the cup or EER for cooling indicates a more energy efficient system, as it provides more heating or cooling output per unit of energy input from the electricity. Okay, so the cup is an important parameter used to evaluate and compare the efficiency of HVAC system. And it can be a useful factor to consider when selecting and designing HVAC system for optimal energy performance and cost savings. Okay, so this is an example of a photo that we take during our visit. So this system was a York air conditioning. Okay, here we see it's a York is the brand. Okay, we have a lot of reference, compressor type, the electrical motor, okay, the capacity, cooling capacity, okay, and we have the capacity in this one. We have the capacity in watt and in BTU per hour, okay. So these numbers are exactly the same thing. They are just expressed in different units. A different unit is like if you 1 kilometer and 1,000 meter. 1 and 1,000 is different, but they are expressed exactly the same thing. One is in kilometer, one is in meter. This is exactly the same. One is in BTU per hour and one is in watt, but they are exactly the same. Okay, don't be confused about that. It's just different units from the same thing. It's what is important is to see that it's the capacity, and you see the COP, coefficient of performance. Okay, and it expressed in kilowatt per kilowatt. So this COP of 2.8, not super good for an air conditioning. Okay, and you can see also here you have the power input. Okay, in watt. So you see the energy of the power input is measured in the same as the cooling capacity in watt. Okay, so if you have only the BTU, you transform the BTU per hour into watt and you get the cooling capacity in watt. And if you compare the cooling capacity in watt to the power input, okay, if you divide, as I wrote here, the 17,550, 580 that you have here divided by 6,240, you have 2.82, which is exactly the coefficient of performance in kilowatt per kilowatt that is mentioned here. Okay. And in this one, we are very lucky because they also mention about the EER. Okay. Honestly, why they write so many information that may be a little bit confusing, I don't know. But actually, you see EER, how do they calculate it? With what I explained, you would be able to do it. So EER, you compare the BTU, okay, per hour, and you divide, so the cooling capacity, but in a different unit, divided by the power input. So you divide BTU per hour per watt, and you have 9.62, okay? And basically, for air conditioning, the EER is always equal to the COP, the COP, multiplied by 3.412, okay? It's very simple because this is exactly the same ratio when you transform. If you want to know how much BTU is a cooling capacity in watt, you multiply by 3.412, okay? So it's just a different unit for the same thing. I am just mentioning here because basically you have engineers that talk about COPs, engineers that talk about EER. You ask a question and they answer EER or COP. And so you have a little bit of knowledge about what it is. Okay, but today, so this one is not very efficient because 2.882 is not, it must be a quite of old air conditioning. And you can see the manufacturing date is 6 years ago because it's 20, I mean, 2060. Today we are in the 2562. But a good one is today is about 4. 4 means that you have for 1 kilowatt, okay, of energy from the power that you use, you can remove 4 kilowatt of heat from the house, okay? So you use 1 kilowatt, you remove 4. That's super efficient. That's why in Europe and in the US, more and more people use a heat pump, because we use less energy and we remove a lot of energy in cooling or in heating. It works the same. You have maybe slightly different performance in heating and cooling, but this is very efficient. If you compare in heating, a boiler, you will use a lot of energy from oil or from gas. You can measure also in kilowatt, but it's not like this. In general, you use even more kilowatts from the gas or from the oil to heat a smaller amount of kilowatt in terms of heat energy. So that's why the heat pump are the future, because it's very efficient. Okay. Any question on that? Okay. So just some units to remember. So BTU per hour is British thermal unit per hour. The cooling capacity is always BTU per hour. And I wrote, often wrongly named BTU, because when you ask a lot of engineers, they say, oh yeah, I have a 60,000 BTU air conditioning. No, it's BTU per hour. It's just like a short way to say the same thing, but it's good for you to know, because in generally, they don't really know, and when it comes to make the calculation, they make some mistakes sometimes. There is also a unit that is very rarely used, is the MBH, is 1000 BTU per hour. I see there is a typo here. So is 1000 BTU per hour is 1 MBH. Rarely used, but in case, I don't know, in the US or some other country they use it, at least you know what it is. The watt, conversion of watt and kilowatt, okay, but 1 kilowatt is 1000 watt. And how to convert BTU per hour to kilowatt, and how to convert kilowatt to BTU per hour. You see 1 kilowatt is 3.412 BTU per hour. So it's exactly the same as this number here, 3.412, okay? Because I already explained. So you can always convert BTU per hour to kilowatt and kilowatt to BTU per hour. Another unit to say the same thing is the refrigeration ton. Some country call it RT, some country they call it TR, some country they call it T. They are the same thing, is a refrigeration ton. Okay, and 1 ton, 1 RT is 12,000 BTU per hour. So you can play the game and convert every cooling capacity in every unit you want. Another one to say the same thing, I just mentioned, because who knows, sometimes you visit a factory and they purchase a system in a different country and they express everything in different units. So now you know how to convert it. Is the horsepower. Horsepower, same as a car, okay? Meaning how much energy is developed by your car, but this is how much energy is developed by your air conditioning. Horsepower, 1 horsepower is 9,000 BTU per hour. Okay. We can find 1,000 of different units, like calorie, like joules. Okay, they are the same, but I've never seen calorie and joules used in HVAC or air conditioning systems. So I just put the one that I have seen being used in air conditioning or HVAC system here. Okay. Any question? Okay, carry on. So now let's get into the details of air conditioning. Okay. How does it work? What is this heat pump? What is this air conditioning? So heat pump is actually a good word because it really describes what it does. Okay, so here, this is the refrigeration cycle. So we have two parts on this drawing. One is inside of the building, one is outside of the building. Okay, so let's say we are talking about, sorry, air conditioning. Okay, so here we have outside temperature. Okay, and here T1, we have inside temperature that is smaller than T1. Okay. And this is where we want to remove the heat. We want to extract the heat from this side, from inside, and remove the heat to outside. How to do that? Why do we use a refrigerant fluid? Okay, so the refrigerant fluid has the property, everything to cool is happening here at the expansion valve here. So here I put that because the expansion valve is a device when you have a fluid that is under pressure and you release the pressure, okay? So you reduce the pressure inside the container. You reduce the pressure in the air conditioning inside the conduit, inside the system. You reduce the pressure, okay? And here, I will stop sharing for 1 second, okay? So here, you have the air spray, okay? And here, we have the temperature. So I don't use the aircon in my house, you see, is 30 degrees. And I put the sensor, here you can see the sensor, one on the top and one on the bottom, just to have a look. So this is air spray. And I will spray, and let's see what it does. So basically, this is like an air conditioning, okay? We have a container full of liquid gas, liquid air, okay? And when I will press here, it's an expansion valve, I will release the pressure. So the pressure will go down inside the container, okay? So let's see what it does. Okay, I've never done it. I say I will do it in live. So let's see. I should not do that. Wow, I can feel in my hand, it's very cold. The time it's, I'm just, okay, that's what I'm doing here. I'm just spraying the air, okay? It's freezing, I don't know if you see, but there are some condensation. And when you see, it's really the temperature has get down. So by the time, you know, I mean, the contact is not very good, so it shows only a few degrees less, but actually, when you put your hand, it's very cold. I don't know if you already did this, but when you release the pressure in a can, from a can like this, the pressure drop. It's super cold, actually. Let's see if the temperature. So we were from 30 to now 24, 25, okay? And the measurement is not super well done, but just to show the idea is that we reduce the temperature, it's still going down, 23, okay? So whatever, we are not here to check the kind of compressed air, but it's to show you the physical principle. You see, it's still carrying on to go down. So I will share back again. So this is exactly what is happening in the air conditioning here at the expansion valve, okay? So this is interesting because what we see happening here, it's on the can is exactly what is happening in the air conditioning at the expansion valve. So it's cold. It's cold because it removes the heat. It's cold. I didn't go into detail, but it's there are a lot of physical law that we can go in detail. Is about what we call the law of ideal gas. That means that pressure multiplied by volume. Okay, here we have some pressure inside this tank, and we have a volume, a fixed volume of the tank, is equal to a constant times the temperature. Okay, the constant is the quantity of mole, and R is another constant, but basically it's proportional. What this law said that is interesting is that the pressure times the volume multiplied by the volume is a constant equal to a constant to the temperature. So when you reduce the temperature at a fixed volume, when you reduce the pressure, sorry, at a fixed volume, this is what we did. We remove the pressure from inside and we get outside. Okay, so the temperature inside the can reduced. But since it is proportional and equal to a constant from the temperature gets down inside. This is PV equals nRT, okay? So this is exactly what happened, and the principle of physics that is used in an air conditioning system, okay? So this is the expansion valve. And so then when you have the expansion valve, you say, well, great, the temperature gets down, so you pass this fluid, this liquid fluid into the evaporator, okay? The one that we saw before that is inside, okay? So you have a lot of, you can see a lot of how can I say, circulation, and with the fin of the copper, okay? And there is the refrigerant fluid inside, okay, that is cold. And that's what we use because it absorbs the energy from outside, okay? And by absorbing the energy, we go from liquid to gas. When we compress here, okay, when you release the pressure, inside it's liquid, okay? But outside, when you release the pressure, it's a gas, right? I didn't spray myself with water, I mean, or liquid air, it was gas. So that's exactly what happened in this place, in the air conditioning. Inside, you have the expansion valve, it was liquid, and it turns into gas, okay? So this gas is a gas. And so you bring it, there is a pump here, you bring it outside where you have the compressor, and you compress the gas, okay? To put the pressure again. Because basically, what we use is we release the pressure from the gas, okay, that absorbs the energy, that's why it's cold, okay? And we use the same gas, okay, because this, if we use air conditioning like this, we need to buy a lot of can to cool the room, and it's not very nice from the environment, so we have to use the same quantity of gas, and we have to compress it again to increase the pressure again in the gas, okay? That's what is happening in the compressor. So the compressor is the gas that we just expanded, okay? So with low pressure, we make it with higher pressure again, okay? And this is where we use a lot of electricity, okay? The compressor consumes a lot of electricity, okay? To compress the gas, to put it at high pressure level again. But when you compress, I don't know if you did that, you use old syringe, okay? And you put your finger on one side and you press, what's happening? It's getting hot, okay? Because of the same law, what is happening here at the expansion valve, you remember pressure times volume is a constant, is equal to the temperature times the constant, okay? So when you increase the pressure with the same volume, the temperature increase, okay? And the temperature increase, we want to remove this heat, so that's what we call the condenser. So the condenser, the equipment is exactly the same of the evaporator. The only difference is that it removes the heat from inside the gas, okay, that is hot, high pressure and hot. It removes the heat to outside, okay? So that's why we have a fan, that blows through the fin that looks exactly the same as the one inside the air conditioning, okay? And we extract the heat from the compressed gas, okay? That's really what we call the heat pump. Because on this side, on the coil, we absorb the heat because we just release the pressure in the gas, okay? And here, we remove the heat from the compressed gas with high pressure, okay? And so on and so forth. After the condenser, after the compressor and the condenser, the gas is cool at the good temperature and at the good pressure, and we release the pressure again. That makes what we just checked with this experience. So this is the refrigeration cycle. This is how the air conditioning works. It's actually very simple. I try to make it like a... Do you have any question? Yeah, Jatin, you have a question?
Hi, Thomas. Very good morning from India.
Good morning.
Okay, please correct me if I'm wrong. Just trying to understand the basic functioning. Could you please repeat the evaporator and condenser functioning again? Because I'm trying to understand the heating function simultaneously. I believe the heating is reversed.
So I explained this just earlier. In the beginning, I can spend some time. So basically, just before you arrived, we explained the heat transfer. So the evaporator, I will explain just very quickly, and I can spend some time with you after. So
Sure.
the evaporator is the place where you have inside the refrigerant fluid that you have the metallic fin, and that will where the heat transfer happens, where you have the heat from the water and the air, okay, that is transferred through the copper of the metallic fins of the coil to inside the refrigerant fluid, okay? So since inside this coil, let's go back here. So inside this coil, okay, we have a cold refrigerant fluid with low temperature, okay? You remember? And outside we have a hot air. So what happened? So here we are inside of the coil where we have the refrigerant fluid with low pressure and low temperature, as we just checked, okay? Here. And here we are outside of the coil, okay, where we have the hot air, okay? So one side we are exactly in this case where we have the air outside of the coil and the refrigerant fluid inside of the coil. So the heat will transfer from the air and the moisture in the air through the copper of the coil until the refrigerant fluid that is cold. What I explained before is the law of Fourier that says that with the thermal conductivity, and if we take one specific surface area, the quantity of energy that we transfer is proportional to the delta T. If you have exactly the same temperature inside and outside, you have no transfer. But since we have a temperature difference because the air of the room here on this side is higher than the temperature of the refrigerant fluid, you have a gradient of temperature, so you have the heat transfer. So we remove the heat from the air and humidity of the air to put it inside of the coil. So this is the evaporator coil. On the other side, if we go on this side, on the condenser coil, okay, we have the same refrigerant fluid, but remember it's high pressure and high temperature because it's compressed gas, okay? So what happened? We are in this case exactly the same. But in this case, we are, here is the gas, the compressed gas, inside of the condenser, okay? We are inside of the condenser if you are the conduit with the gas here, okay?
Got it.
And outside is the air, okay? But the gas is hotter than the outside. So through the copper, the heat is transferred from the gas that is inside to the outdoor air, even though we feel it's hot because it's 35 degrees, but actually the gas is much hotter than this when it's compressed. So we transfer the heat through the coil. So it's the same tool, the same coil, but one side you transfer from inside to outside and the other side to outside to inside of the coil. That is exactly what it's called a cycle, because we use one amount of gas, we expand it and we compress it to absorb the heat and to remove the heat from one side to another. Okay. Any is it clear? I mean, it's, yeah. Any question?
Yes, loud and clear. Thank you so much.
Okay. So now about different types of air conditioning. So it was invented. I will not explain the entire history of the history, but it was invented in the US. And the first type of air conditioning are this type, what we call window type. Okay. So basically, you can see from inside, the view from inside on the left here, this area basically is the air return. So you have the air coming inside, and this area on the top is the air supply. So you have the air going out this side. Okay, air inlet, air outlet. Okay, and in the middle, if you look this part, so you have the hot air, hot and humid air coming inside, and the cold air, this is going through the evaporator. So we are exactly in this case, these are exactly the same thing, okay? Pass through the evaporator, the air pass through the evaporator, because in the middle you have a fan, a blower that sucks the air and is blown out after being cold, okay? This is what is happening inside. And in the same machine, on the other side, where you have the condenser, you see? So once again, we are exactly in this condition. This is exactly this. In one machine, but outside. So takes the outside air from the top here. You can see here from the outside view on the right side, you can see this grid here. So here you have the air that is warm, but colder than the gas, the compressed gas, okay? That is getting inside, and that is blown with a fan outside through the condenser, okay? So we have exactly one box that does both parts, and that we call window type, because you can put it into the window. You have the outside part and the inside part. So that was very efficient, very compact, one in all. That's very good. The problem with that was that it was very noisy, because the compressor here, you see, you have the compressor, huh? You have all the equipment, and you have the expansion valve somewhere. Where is it? Somewhere here. You have the expansion valve, but the compressor makes a lot of noise. And since it is in the machine that is basically inside your house, it was very, very noisy. And from now on, I will, you will always see on the top right corner of the slide here, one type. This is direct expansion, okay? Direct expansion. Why expansion? Because here we have the expansion valve, okay, remember, okay? And direct expansion, that means this, we expand the gas and it's direct cooling the air, okay? So it's direct from the gas expanding to the air, direct. And the other type will be chiller type, which was exactly the same principle, but there is another step, another stage, where we cool the water before moving the water. So we have multiple stage basically, but this one is direct expansion, window type, okay? Basically, all the machine we will see direct expansion, they are exactly the same, just separate, split type. That's why we call split type, because they are not window type, they are not one block, they are separate, split. One is outside and one is inside, okay? But we have always the same principle. Okay, you can always find the compressor, the expansion valve, the outdoor coil with the fan, of course, that is not represented here. The evaporator coil. Okay, air in, air out, air in, air out. So this is exactly the same, but this is what we call the split type. So this is important because in general, at least in Thailand, when people say split type, they only see this kind of unit, you know, the wall-mounted split unit. But actually, it's extension of language, but it's wrong. Split type means that you have two separate areas. One is outside, the compressor and condenser is outside, and the evaporator and expansion valve is inside. And they are separated. And they are just linked with the conduit for the refrigerant fluid in and out. But they are split. They are not in the window type where everything is in one machine. So whatever is the indoor unit, okay, it is a split type. You can have a four-way cassette, you can have a AHU, you can have a FCU, you can have a ceiling mounted. It is a split type. Just for your very good understanding, because I believe that not a lot of people know about that, but it is important because sometimes when you communicate with your clients, we have to ask a lot of questions, and the way they answer, we have to imagine that they don't know that, and we have to, to understand. So that's what is written here. In opposition of the window type, the air conditioning, in opposition to the window type air conditioning, the split type air conditioning is composed of two separated split parts: outdoor unit, compressor and condenser and fan, and indoor unit, expansion valve, evaporator, coil, and fan. And what is important to know also is that these parts represent 80% in general of the total power consumption of the system compared to inside. Okay, this one is just about 20% to make it simple. Okay, of the total power consumption. Okay, of the area. So when we talk about COP, you remember COP before, how much electrical energy we use to remove the heat energy inside. The COP takes into account the total amount of energy of all these this entire system. Okay, and this is important. I will tell you why a little bit later. Something that is also important, just to have a generic idea about how it can be installed. So you can have one compressor condenser for one unit. This is what we call monosplit. Or you can have one compressor condenser unit that brings the refrigerant fluid into multiple indoor units. Okay? And this is what we call multi-split. And you can have a bank of compressor and condenser units. That means multiple condenser and compressor units in a central system that their job is to produce a lot of high pressure gas, okay? And then after they have a different distribution of this gas to the different indoor units. So you have multiple configuration, but they are all working on the same system of one by one, okay? So this is what looks like on the split type, an outdoor unit. So basically they are compressor. Here you have some real case photo. They look different depending on the brand, depending on the capacity, but they all are the same. They are the condensing compressor unit, okay? We have different type of compressor, what we call on-off, which are non-inverter, okay? With a fixed speed of the compressor. That means the compressor, when the compressor is on, they have only one speed, okay? So you compress the gas, whatever is the need, you compress at the same speed, okay? This is non-inverter, okay, on-off. And you have also variable speed type compressor, which is more energy efficient because the speed of the compressor is not the same and can be adapted to the need. So if you have a lot of heat inside the house, okay, you will have a lot of need to compress, you need a lot of gas, okay? So you need high speed of the compressor. If the heat is lower, you need less gas, so the speed is lower. If you have a lot of heat, the speed is higher. If you have a small heat, the speed is lower, okay? So that is more energy efficient because the speed of the compressor can be adapted. And what we call inverter is just because to make the compressor speed variable, we use an inverter. Inverter is just the electrical technology that can adapt the speed of the motor of the compressor, okay? So inverter, non-inverter, and related to energy efficiency. Some brands have also different names. VRV, when instead of calling inverter, which is a generic name for the technology that makes the speed of the compressor variable, they call it VRV, variable refrigerant volume, but it's exactly the same. The compressor variable speed, but you have different volume, variable volume of gas. So they say variable refrigerant volume. So it's a different name for the same thing. Or VRF, variable refrigerant flow. Okay. So there are different names for the same principle. Sometimes the technology, depending on the brand, is a little bit different, but they do the same thing. Okay. So this is an explanation. Do you have any question on this? No? Okay, I'll move on. Next, I explain what is a multi-split. So what I was just quickly mentioning, you have one outdoor unit, one compressor that can bring the fluid to multiple indoor units. They can be all the same type or all different, doesn't matter. You have one indoor unit for several, one outdoor unit, sorry, for several indoor units, okay? This is important for us because when we want to do a proof of concept, okay, we need basically to measure how much power we use for the complete system, okay? How much power we consume before we install continuum, okay? Sorry, I'm very poor in handling my mouse. So we need to quantify how much power we use before and after, but we have only one system, okay? So in this case, because you remember I told you this is 80% of the power consumption, okay? We have to equip the entire system in a multi-split, okay? So we have to equip, we have to measure before the entire system, okay? And we have to equip after and all the units inside. So just be careful when you ask someone, oh yeah, it's a split system, this is a split system, okay, you can only equip this. Yes. If you don't ask any more questions, that's the answer. You say, oh yeah, I will equip this one, I can make the test. And then after I say, oh, Thomas, we didn't see any results. Continuum don't work. No. What is happening is that maybe you didn't see, or you didn't ask the question, or you didn't check because even the engineer that just arrived in this property doesn't know. Okay, but you have to check that maybe you have one compressor, but that does not power only the one that you use, but powers also many others. Okay, that can be in the same room with other systems, so we have to take everything in the room, or can be in separate room. So you have to equip the entire system and control the parameter everywhere in every room because you have one compressor. But depending on the question you ask, don't forget to check this also. Because if you measure the power here and you equip only one air conditioning, you will not see anything, or you will see very, very poor results. But when you ask the question, sometimes the answer, genuinely, people don't know, and they answer your question. What they say is right, but it's not complete. So this is another system, is central split type system. So it's exactly the same as before. The only difference is that you have here not one compressor, but many compressors working together. Okay, so there is an algorithm that says, okay, I need 1, 2, 3 variable speed, variable quantity, super smart, that produce the refrigerant fluid, okay, to many systems, okay? So you can have here a 2-way cassette, 1-way cassette, 4-way cassette, ceiling mounted, floor mounted, wall mounted, AHU, FCU. These central split systems exist. We have more and more. They are used more and more because they are energy efficient, because you can manage and adapt very well the load of the compressor, so the energy consumption, to the need inside the room. But the same question, the same point that I made before is valid here as well. We have to understand this, how is the setup of the air conditioning system at our clients. This is what we need to understand. Because depending on the situation, when you make a proof of concept, you have to know this, because then it will define where you have to measure, where you have to equip, and if we can do it or not, because one of them maybe is in a warehouse with permanent open door, something like that. So this is what we have to check, okay? Any question? No? Okay. Good. And this is a situation that I found very interesting because it's a mix of everything, okay? Always the same principle, but this is just to raise your awareness and make you aware of what can happen and what you have to check before a proof of concept, okay? So you have this area, this system here is a centralized split system with multiple compressor that brings some refrigerant fluid to many indoor units. You can see on 3 different floors, this floor, but also this one, and even the basement, okay? So this bank of compressor brings some refrigerant fluid to 3 different floors, okay? And here we have other system, you have one single split, okay, here. So you have one compressor that brings just into one room here, okay? So this one is easy. And you have here, because you have two separate compressors that brings fluid to one indoor unit, okay? So this is what we need to know, because if you want to make a measurement of a proof of concept, where would you do it? Who have an idea of where? Yeah.
The best place would be to do it on the very left split system with the one compressor outside that supplies the one indoor unit in
That
this
one?
specific room.
Yeah, exactly. Exactly. Because
Yay,
it's
continuum
easy.
for 5 years. I learned something.
It's interesting because basically you have one power meter to measure, and you have one single room here, okay? So you can control and you have the complete measurements. If, let's say, this air conditioning unit was there, okay? If you would like to measure, to make a proof of concept here, okay? In this top floor, big room, then it becomes complex because first, you have to measure here, but here measure the 3 floors, but also you will have to add this one. So it's becoming very complex to measure and to know what we are measuring. We need to measure the power consumption of the place. Another thing that is interesting in this slide is here. So you have the fresh air. Okay, so in here we have a fan basically that brings fresh air. You see the dark blue arrow here is the outdoor air with full of oxygen, okay? And air extraction with lots of CO2 that goes outside. So these are also parameters to control when we make a proof of concept, because we need to know how much fresh air from inside we bring to make sure that it's stable, and to make sure that we put continuum there as well to improve the performance. Okay. Now about inverter and non-inverter, I speak already a little bit about that, just to make it more with figures. So they definitely look really the same. So here we have the same brand, Daikin, for example. This one on the left side is non-inverter, and this one on the right side is inverter. So at the first look, it's very difficult to say if it is inverter or non-inverter. But it is pretty important, because depending if we are non-inverter or inverter, we know that continuum will bring different sets of energy savings, okay? So when we have a non-inverter, basically, as I mentioned, you have the compressor has only one speed, and it's on or off. That means full speed or stopped, okay? And therefore, you see the temperature here in the orange line is the temperature inside. So you see when the compressor is on, the temperature goes down, okay, until it stops. Then the temperature goes up. Then it's too hot, so the temperature goes down again because they start the compressor, and so on and so forth, okay? With an inverter, the compressor is on full speed at the beginning, okay? So consume full power. The temperature goes down fast, okay? Then after you get near to the temperature setup here, the temperature setup in this line, okay? You're getting near, so it starts to reduce the speed to save energy, okay? So the speed goes down, so the power consumption goes down. The speed of the temperature decrease going down, okay? And then after, it adapts the speed, you see, going down and increase a little bit, decrease, increase, decrease, with much lower energy than a split type, than a non-inverter type, sorry. And then you have a more comfortable temperature, okay? And you don't have this big peak of hot and cold, okay? So you save energy, it's more comfortable. So that is inverter. So we know, sorry, in a non-inverter, we saved on average 25%. On an inverter, we save 15 to 20%, okay? In normal conditions, all right? So this is important to know when you make your proof of concept and projection of savings and ROI calculation, to know this in advance before even starting the proof of concept. So they have a figure of what would be the ROI and payback of their system based on the technology they use, okay? This is real case example of how a non-inverter is functioning. So these are the same temperature sensor as you see in my camera here, okay? So you have two temperature recorder, one recorder, but two channels. One we put at the air supply, and one we put at the air return of the indoor unit. So the yellow line is the air supply, so you can see that the temperature of the air supply is getting much low, and then after rise again and getting low, decrease and increase, decrease and increase. So this means exactly during this time, okay, tac, until here. So you can say that the compressor is on, okay? So when the compressor is on, remember the refrigeration cycle, we put pressure on the refrigerant fluid. So there is a lot of pressure. So the expansion is very powerful. So it's getting cold, okay? You extract the air, the heat exchange that I explained. All of this makes sense now just with this line, okay? Because you can see, okay, we start to get high pressure refrigerant fluid that is expanded, the temperature drops, okay? Then after you reach some maximum level, depending on the refrigerant fluid and the capacity of the system, okay? You reach, at the same time, you see the room temperature was high and decrease fast and stabilize, go down, 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 up, just reach a minimum point, what we call the compressor offline here. You can see on the right here. And that says the system say here, you trigger, you reach this temperature, I trigger the compressor and I give in the information to stop. So the compressor stop. So when the compressor stop, of course, there is no more refrigerant fluid coming out, okay, from the expansion valve. So the temperature of the air supply is rise. If the temperature of the air supply rise, the temperature in the room rise until reach this point, okay, what we call the compressor on point, okay. And when you reach this temperature up, the system says, hey, temperature is too high, I need the compressor to start again. So between this line here, so here we have the compressor is off, okay. And then from this point, when you reach this temperature setup, this temperature line, okay, for the setup, when you put the setup, the system actually, when it's non-inverter, has two temperature, compressor off, compressor on. And then after, when the outdoor temperature reach the maximum accepted temperature, then start again the compressor. So the compressor is on again, and so on and so forth. Okay, so you can see, and you can see that it's not regular cycle because sometimes you have more heat to remove. Sometimes you have more sun, so you have more heat. Sometimes you have more people. Sometimes you have less. Sometimes you have a cloud. So we don't have always regular cycle because we are in real life. But this is how to summarize how the refrigerant cycle is working. Do you have any question? No? Okay. Now, something that everybody loves, chiller system, okay? But I tell you exactly, it's exactly the same, okay? The only difference is that there is one additional stage, okay? In general, there are several chillers in a property, okay? Because they have basically, it's a central system. So if the system breaks, the entire building don't have air conditioning. So that's why they have multiple chillers, okay? And depending on the cooling capacity that they need for the entire building, they need several chillers as well. So in general, it's never two, it's always three, one spare and two functioning, 3 or 5 or 7, okay? But the principle is the same because what you have here, you see, okay, what you have here, what is it? What it looks like? It looks exactly as a compressor or the split type of we are here. It's exactly the same. This is the same. This is the same. The only difference is that here, the evaporator, okay, this part here, in a direct expansion system, this part is in the air, okay? In a chiller, this part here, so here we have the condenser, we have the expansion valve, we have the compressor, so you have a refrigerant fluid here, but the evaporator, that I will name E, the evaporator, instead of being direct in the air, is inside water. So it's cooling water. Instead of cooling air, it's cooling water, okay? So we use the refrigeration cycle, not to cool air, but to cool water. They are exactly the same mechanical part, exactly the same system, just adapted to cool water, but it's exactly the same. And you remember the condenser in a split type is outside the compressor, and the condenser to take out, to remove the heat, okay? But in a building, it would be impossible and too big. So they put the condenser into water as well, okay? And we have a system to cool the refrigerant fluid that is in the condenser with water. Instead of being cooled by air outside, we cool with water, okay? And the water is circulated to a cooling tower, so we cool the water that cool the refrigerants, okay? So we have a heat transfer, basically, okay? Inside the chiller, we remove the heat from the chiller, okay? Inside the chiller, you have water. We remove the heat goes into the refrigerant fluid. And here in the condenser, we remove the heat from the refrigerant fluid inside this water that is the water cooling system for the condenser, okay? We cool the water with a system that is called the cooling tower that are on the roof, okay? And then the refrigerant fluid is cooled and gets back to the chiller to cool the water in the chiller. This is the first part. The second part is the water that will be used inside here in the chiller. You have a heat exchanger, so you have cold water, okay? And we use this cold water to go into the AHU or FEU or four-way cassette or whatever, but instead of having directly the evaporator with the refrigerant fluid expanding, we have water. So it's not direct expansion, okay? It is with the water because we cool the water and we use the water, the cold water, to bring into the indoor units. And here we absorb the heat from the room, okay, and bring the heat inside the coil, inside the water. Well, there is a tank in the middle because we use water. And so the water at the inside, at the intake of the AHU or FEU or whatever is cold, and at the outside is hotter, okay? If you take the different temperature, the temperature is hotter because you absorb the heat from the air in the AHU, okay? And then after, go back to the chiller to cool the water, to get the water being cooled by the refrigerant fluid, okay? So if you compare these two images, you realize that you have exactly the same physics principle, okay, into a chiller or into a direct expansion unit. I will go a little bit further, and if you have questions, you will be more than welcome. This is another way to we zoom only on one part of the chiller to say exactly the same thing. So we have the compressor. You remember the compressor is what is used a lot of energy, okay? And you have the same system. Here is the water on the left side. You have the water from the AHU in the room that are going, the water here is going into the chiller to be cooled, okay? So the water gets cooled and gets back to the AHU inside the room. Okay, here we have the room, the AHU here, and the water gets cold and gets back here to the chiller to get cooled, okay? And then we have the cycle, how to cool the water from the chiller here with the compressor, okay? And the heat is transferred to the water, and the water is cooled with the air, the cooling tower, okay? This is what looks like a cooling tower, okay? So a cooling tower basically is just taking the cooling water here. Sorry, take what? Can I? Hold on. Try to erase the link. Okay, take. So here we are zooming on this area, okay? So we are talking about the cooling tower that is used, basically it's the compressor of the same function of the compressor of a split type system. But instead of having the air outside going through the condenser coil, we have the water, and this water will have to cool because we work in closed loop, okay? We don't use water from the city to cool the condenser because it will waste so much water. So we work in closed loop. So we use the water to cool the condenser down, and we have to cool the water. And how to cool the water? We use this system. So this system, you see this big thick conduit, okay, that brings some water inside. You have also some water going from the top, okay. So you have some some system inside where the water, here you have the same, the water is dropping in small drop through this kind of network with a special material, okay? And you can see there is air that can be the air can be taken intake here, okay? And you have a big fan here, and that extract the air outside here. Here you have a big fan that extract the air, and in the middle you have this kind of network, okay, where you have all the water spray in a small droplet, the water that you take from here, from the condenser of the chiller, okay, that is hot. So you bring this hot water on the top, you spray it through this network. With the fan, you suck the air from outside that pass through the water, that cools the water, the air from outside cools the water, okay, a few degrees, and the hot air is extracted here, okay? And you have exactly the same on the other side, it's just look different. The air from outside, the water droplet coming here, so the water here up, you supply the water in fine droplet all around, okay? You have the air, and here you have a big fan. The air is passing, getting here, passing through the water droplet, cool the water droplet, and extracted here. So basically, and the water then is taken back on the water, goes to a different circuit when it's cooler. So the water is dropping on the side, getting cooled by the outside air. And inside here, you have a tank. Okay, I didn't take a photo. Next time I will do. You have a tank of water, and the water gets back to the system. Okay.
I have a question. Sorry, this might seem silly, but let's say this is obviously a chiller system for air conditioning, right? So obviously, if you're using the air conditioning, we would assume that the outdoor air is really hot as well.
Yeah.
But so how would the hot outdoor air that's passing through cool this water? Because the water is way hotter than the outdoor air. Is that what it is?
So not always, but by the principle of I did not get into detail, but here, first slide, there is the vaporization process. When you have a very small drop of water, okay, it has the capacity to absorb the heat to evaporate, okay? And by basically the small drop, they don't disappear because we need to collect this water, but the outer part of the droplet, they vaporize, and by vaporizing, because of the wind, basically, even if the air is hot, okay, it's not like 200 degrees Celsius at least, and you have some vaporization process that happen that cools globally. You cool down the air like this. You cool down the water like this. Did I answer the question?
Yes.
Okay.
Thanks.
So this is outside in general on the roof. And inside you have this marvelous piece of technology, okay, with a lot of conduits, with a lot of terms and a lot of machine. And you say, wow, what is this jungle? It is not a jungle, okay? So CDS stand for who guess? Who has a guess? You have one free net to win if you tell me what is CDS. No, nobody? Too bad. Okay, so CDS is condensing water supply. Okay, so this water in this yellow big conduit is coming basically from the bottom of the tank here, from the cool water, okay? Is going inside the building and goes in here, okay? So this is basically the cold or warm. It's not cold, but it's cooler than it is before, okay? That goes into the condenser. So here you see this is basically a tank. Inside, you have the condenser, the same coil that you see here, okay? The same coil of this, okay? But instead of being in the air, you have it inside this tank, okay? Here you can see this copper, you see this copper conduit here, the one that I highlight on the left, okay? You see it. But this one is the refrigerant fluid. So you can see it's much bigger than in an air conditioning, but you have to cool a full building. And this is the compressor, okay? So you see it's an air conditioning. You have the compressor, the refrigerant fluid. The refrigerant fluid goes out from the compressor, goes into the condenser. The condenser is not inside, outside in the air, it's in the water to cool the water okay, here, because we have to cool the refrigerant fluid by using the condensing water supply from the cooling tower, okay? And here, so this one you see goes at about this level, and at this level, after removing the heat from the compressed gas from the compressor, okay, the water from this condenser of the chiller goes up here, and here you have CDR, condensing water return, condensing water supply, condensing water return, and this line goes back to the cooling tower. So this comes to the cooling tower. So the principle that I explained before in the slide here. So you have the air, the water arriving and the water going back. The water that is coming back from the cooling tower is colder than the water that we send to the cooling tower from the condenser of the chiller that is warmer, okay? So this is the part of the bottom of this. And then, so here we cool the, basically this is the outdoor compressor, okay? So you have the refrigerant fluid, we cool it down with the water from the cooling tower, and we send somewhere, I mean, it's difficult to see, but somewhere you have the refrigerant fluid here that is inside, going through the coil, getting cooled by the water from the cooling tower, getting inside, this part, which is the chiller, okay? And here we have the evaporator. So the evaporator will release the pressure on the gas. Remember what's happening here is exactly the same, but instead of having the coil inside the air, we have the coil inside water, okay? And the water, so we have the water coming here, CHR, is chilled water returning from the AHU, from the FCU, returning from all the system that you have in the building, okay? So the water is hot because it removes the heat from the air, okay? So the air is hot because it absorbs the heat from the air through the AHU, okay? And FCU and all of this. So it's chill water return, so the hot water, okay? Passing through the evaporator with the refrigerant fluid, okay? So the water gets cold, okay? And the cold water is supply here, we don't see, but here is chilled water supply, CHS, and supply to the fan coil unit, FCU, AHU, whatever you have using the water to cool the air. So this is basically how a chiller works. So it's getting big because we work on big capacities. Remember the first slide also, the cooling capacity depends on the size. So the size is big. We have multiple systems. We have pumps because we use water and not air. We have, so there is a lot of electronic, a lot of valve, a lot of temperature sensor, blah, blah. It looks complex, but the system, the principle are exactly the same. Okay. So we don't need to be a highly qualified engineer of carrier or decking, but the principle are here. Any question? Okay. And this is from the other side where you see very clearly. So this is the condenser. Okay. We see the other side of the compressor here. Okay. So we see also that here, the refrigerant fluid goes into the condenser to get cooled. You remember, same as in the split type. Okay, and then after, somewhere here, we see going into the chiller, okay, to cool the water for the chilled water supply, okay, that goes into the FCU, AHU, and so on. Okay, so it looks complex, but actually, it's not so much. So that was on the chiller part. Now on the AHU, FCU, what it does. So here we are coming, okay, from the chiller. So the water is cold, okay. The water is passing through the coil, okay. So the coil looks exactly the same as, I will show you, tac. The coil is exactly the same as a split type direct expansion, except that instead of having refrigerant fluid with the expansion valve, we have the cold air. But the idea, the cold water, sorry. But the idea is, if you remember the first slide, we just transfer the heat from outside through the metal of the coil to the cold water. We have a delta T, so we absorb the heat. Okay, so that is what happened here. We have a cooling coil, and after the cooling coil, the water through the pump, okay, goes back to the chiller because the water now is hot. So you go back to the chiller to get cooled again to what we have seen, and so on and so forth. To regulate this, because when you have an air conditioning, you can put 23 degrees Celsius or you can put 26, okay? And that will have different functioning points, and you need to regulate and make sure that everything is well regulated. So to regulate this, there is a valve here, the chilled water valve. This is very important because this is the one that will regulate how much water you consume from the chiller, okay? So basically, how much energy you consume, okay? You don't use, here you use power only for the fan, okay? You use the power for the fan to suck the air and blow the air inside the room, okay? But this is only 20%. The big energy is from the water. You remember, I give you some idea. Here we measure kilowatt, okay? Water in general, we will measure in ton or in BTU per hour. You remember all this? Now it's getting a little bit more clear. So you have this chilled water valve that regulates how much water gets into the coil. And this is what we have to measure in a proof of concept. We have to make sure that the chilled water valve is functioning well, okay? And we have to make sure that we can measure how much energy this AFCU may absorb from the chiller. So this needs a special device that is called a BTU meter, okay? A BTU meter. Sorry, I write very poorly with the mouse, but I need to find another way, a smart way to do that. But you install a BTU meter to measure how much energy from the water this AHU is absorbing, because this is 80% of the power consumption. But it's difficult to do with the chiller, because if you want to do only on one AHU, the chiller maybe has hundreds AHU, right? So if you measure the power consumption of the AHU, you would have to equip the entire, if you want to measure the power consumption of the chiller, you would have to equip the entire set of AHU, FCU, and so on and so forth. But if you want to do only in one floor with one AHU, then you have to use a BTU meter. I think that was a question.
Yeah, Thomas,
Yeah.
Jatin, I had a question.
Yes.
So I'm in touch with one of the properties who are who have the same setup with the chiller suppliers and AHUs. All right. So this was yesterday when I spoke to them and I was trying to understand their setup, where they mentioned something about dampers for fresh air sources. So these fresh air source that we have, the inlets, do we also have to measure the amount of fresh air coming in order to, carry out the POC process?
Yes, that's a very good question, because here, so it's not represented here. So here, there is what we call the damper. Okay, a damper is kind of an area that you can open or close. Okay.
Yes.
They are like curtains that you open or close that will regulate how much air from outside you let inside the system. Okay. And we know that the more fresh air, what we call outside air, we call fresh air because it's fresh in oxygen, not fresh in temperature, but fresh in oxygen. But the more fresh air we put, the less performance we might get through continuum because we have more moisture coming in that was not processed through the far infrared ray from the net and so on and so forth. So we have to make sure that we have the same before and after, and that it's not like over 20%. Otherwise, we will have very poor performance. And normally, normally the fresh air is 5 to 20%. But we have to make sure that nobody will modify during a proof of concept when we compare when we compare the performance that the fresh air was the same. Okay, this is very important because it can have a very big impact.
So,
Okay.
so you mean to say that dampers, like you said, control the fresh air source inside the given area?
Yeah.
All right. So when we are carrying out, so we're considering the entire property for the POC. So I believe we wouldn't be requiring a BTO meter for that.
For the entire property, no, you just monitor the chiller.
Yes.
You have to make sure that you equip everywhere. And some damper are regulated because basically the idea is to bring oxygen. Okay.
Mhm.
If you are in a big building, I think I know which building you are talking about, with a lot of offices, then the damper are in general regulated automatically, and
Right.
they measure the excuse me, talk too much. They measure the quantity of CO2 inside of the office. So sometimes we have sensors that measure how much CO2 you have in the building, okay? And if they have too much CO2, then they open the damper automatically and bring some more fresh air. So we cannot block the damper,
Right.
okay, in this case, but if you have the same amount of people inside the room before and after, then you have the same amount of CO2, more or less, so you can say that you are in the same condition. Just have to make sure that the system, the regulation is working well in the damper. Also, the outside air, I think I have a photo that will show what you are talking about. We have to equip also continuum in the outside air, but I will call later. And
So with that
yeah.
said, I think our energy validation in terms of savings would not be as much as 20%, maybe slightly less, right?
Yeah, I mean, the quantity of outside air in general is 5 to 20% of the total amount of air that goes into the building.
Okay.
Okay.
All right. Got it. Thank you.
And the rest of the air is coming from the air return. That means the air that we take from the room that we cooled, from the building that we cooled, and that is processed through the air filter, the cooling coil, and so on. There was a question I think I read in the chat. Sorry, I missed that, about where to install the BTU meter. So basically, you install it here. The BTU meter, you install it on the water pipe that brings the water from the chiller to the cooling coil of the AHU, and on the water pipe that takes back the water to the chiller. Because the BTU meter, if you remember this slide is very important in many aspects, and will answer this question. You remember this, the quantity of energy is proportional to the delta T, okay? Here you have T1 that is hot and T2, okay? So if you want to measure the quantity of heat, that means the energy that is consumed by your AHU, how much the water absorbs the heat, okay? Which will result in the end on how much the power consumption of the chiller, okay? You need to measure the delta T. And here, the delta T in the chiller here, you have the temperature that is coming from the chiller and the temperature that is going back to the chiller, okay? So you absorb the heat. Here you have the air from outside that is hot, the air from the office coming back that is cold. So you have a pretty hot air, okay, that you have to cool, okay? And you absorb the heat with the water inside the coil. Okay, and to measure how much heat you absorb, you need the BTU meter. So you plug it into the BTU has to measure the temperature of this water line and also the temperature of the return, the chiller return water. Okay. So by the delta T and by the Fourier's law that I showed before, the BTU meter, and with the flow also, we have a flow meter. What is the quantity per minute or per hour of water that is processed? That will be regulated by the chiller valve. So the BTU meter is installed in 2 lines. So it plugs into the 2 lines. But this conduit can be big, this can be small. So to choose a BTU meter, it's a costly equipment that is very interesting and important if you want to control the energy that your system is consuming. But it really depends on the size of the thickness and the thickness of the conduit that brings the water to the coil and brings the water back to the chiller. So this is where we install the BTU meter. Did I answer your question, Simon?
Yes, yes, and I understand the answer.
Okay.
Thank you, Thomas.
Okay. So this is, I think Jatin will recognize this one. So this is basically the system that sucks the air from outside. So this is here, we are here, okay? And this here, you have the air. It's can become complex. I will not explain everything, but takes the hot air from outside, okay? And extract, also you have a system that extracts the air from inside, but the air from inside the building is already cold, so there is a heat exchange to absorb the heat, to absorb the heat from outside, thanks to the air that is cold from inside, okay? If you open here, it's quite a complex system, but basically you have also a heat exchanger, and sometimes they put, like you can see here, there is some water conduit, okay, that brings some water from the chiller. So that means that the chiller consumes energy to cool this water, okay, and to that will return from the chiller. Sorry, one is water in, water out. So this consumes energy also to cool the air from outside. So it's a pre-cooled air unit. It's air handling unit, AHU, but to pre-cool the air from outside. So they pre-cool the air from outside with the chiller water, but also with the air extraction from inside. So just mention you this, so you are not surprised, but you have to understand this and ask your client if they have this kind of system, because if they have this kind of system, then we have to install the net here as well. Okay. And these are different kind of AHU that you may have, different way they look. Okay, so they are inside. You can see big conduit that brings back the air from the office, for example, and some part can be the air from outside from the place I just showed you. All is mixed here with a damper. Okay, how much we open or close the air from outside. Okay, and this mix will go to the AHU that will cool the air from the water chiller. Okay. And sucks also this might be the air supply, and sucks the air from here and blow. Well, that was a bit of a mix. These are some different models, so it looks similar, a little bit different because you have different kind of filter. I will come back on the filter, but you can see always that behind the filter, so here you have the filter, and behind the filter you always have the coil. Okay. So this is the evaporator coil with inside the water from the chiller. You may have multiple layers of filter. In this case, you have the one filter, first filter, preliminary filter, and secondary filter. Okay. Here as well on the right side, you have preliminary filter, that is a fiber filter, and secondary filter, that is bag filter in this case. Okay. But always behind you have the coil. Here you have the coil here, and here we cannot see, but it's behind the bag filter. This is just to show you so you are not surprised when you visit. where we have to install the net is always the closest to the coil as possible. So sometimes it's easy, like in this case, when we have one metallic filter where we can easily attach continuum, okay? Sometimes, like in this case, it's not easy because on the left side, you see, here you have a pre-filter and here you have the back filter. And we should install continuum here, like close to the coil, but there's no place to attach, okay? So that's where either we choose and decide to make a metallic structure, modify the system, and find a way to attach continuum on the existing structure, and finding a way to do it if it is possible. But it has to be done carefully and professionally so the continuum net don't touch the fin of the coil, okay? Because we cannot attach to the back filter, okay? When you see the way it looks, it's impossible. Or what we do, we install in between the two filters here, between the pre-filter and the back filter. It's not optimum, but that's the best we can do sometimes. This is another example of, you see, if you look at here, you have actually 2 layers of filter. So we decided to put continuum in the middle of the sandwich of the 2 filters, okay? Because it was difficult. The structure of this filter is paper, so you can see on the right side, you can see the paper is not very strong. You can see it's the deformation. So attaching continuum here, you might break the paper, and continuum can flow away and touch the coil and have no efficiency anymore. So sometimes it's better to put it on the opposite side or build a structure that you can attach on the frame here of the existing system. So it's always, every AHU is different, and you have to get this principle in mind to find out where is the best place to install continuum. The ideal case is this one, where you have a metallic or like a strong filter, and we attach continuum at the back of the filter. And you can see here, this is the evaporator coil where you have the water from the chiller, the evaporator coil, and here we have the continuum net back of the filter, and the rule is as close as possible to the coil, okay? That's what I explained before. Here you see better, on this photo you can see better the 2 layers of filter in this case. So we have the evaporator coil here, okay? Evaporator coil, 1 filter, and in between here, this we open, we remove only 1 layer of filter, we put continuum. But that's not the ideal. But sometimes we have to adapt. Different unit that you might see, okay? Split unit. Remember, split is when it's separated from one single machine. So all of these models that you can see here, they have names that I would like that we all use the same name: wall mounted, 4-way cassette, floor standing, fine coil unit, FCU, large FCU, large fine coil unit, floor mounted, 1-way cassette. We have 2-way cassette. We have a lot of different models, ceiling mounted. All of them can work with direct expansion, remember the refrigerant fluid directly, or with the water from the chiller. They have different references because the evaporator coil is different, because you don't have the expansion valve with the water, obviously. You just have the regulation valve, is different, but they look exactly the same. So this, when you see this, it doesn't mean that it's a direct expansion with a compressor, because you can have heat power with the water from the chiller. In general, this model is used with compressor, but it's just in general. You have case where you can have water from the chiller. Okay, Where to install continuum? So this is a very simple. The closest to the coil as possible in the wall-mounted unit. In this case, we place it on the top of the filter. The reason for that is that there is no plastic protection enough to prevent the net to touch the coil, and the net should not touch the coil. So we put it above the dust filter. Okay, if you have like some plastic structure here more to prevent the net to touch the coil, then we put it below the dust filter. But in this case, we place it above. But this is very close to the coil, so it's okay. Okay. This is an example of ceiling mounted. They are exactly the same as floor mounted. They are just in a different position. One is in the ceiling, one is on the wall, on the floor. So these are very simple. You open where you have the dust filter, you cut the net, you put the net on the top of the dust filter, and you close. End of the story. There is no nothing else we can do, and it works well. This is how to put it onto So this is how to put it on a 4-way cassette. So this is very simple. Basically, you open, you have the dust filter that you can see, okay? And you place the net on top of it, and you close, and that's finished. Just remember always to warn the maintenance team that there is a filter, that they should not throw it away, and that they, when they open, we might want to attach it with a zip tie to make sure that it doesn't fall. When it is for a POC, we don't do it. But just another way to install fine coil unit. Basically, it's a small AHU. They just look different. Something that is interesting to know about fan coil unit. So you have the same devices, okay? You have the fan, you have the evaporator coil, and same, you can have water, or you can have the refrigerant fluid, doesn't matter, it works, we have both situations. Okay, and something that is important is this, that I would like to highlight, is the plenum, okay? So this is a photo. So the air here is blown this way and sucked from there, okay? In general, when it's well done, here is ducted. That means you have a big duct into a specific material to bring the air to the room in different places, okay? And on the back, you have this plenum. The plenum is a kind of box where you can put the filters. So this is very efficient because here we can place, you have the dust filter, okay, on the back where the air gets in, and we can put continuum here very easily. It's very well attached and it's very close to the coil. So we have a very good efficiency like this. Here you can see this is the back of an FCU. So when you look from outside, sucks the air from above the ceiling. You remove the filter, you install continuum on the filter, you place the dust filter on top of continuum, and you put it back, continuum facing the coil into the FCU. You have different kind of filter. They looks like this here, but same, you attach to the filter and you place it back on the FCU. That is the ideal case, okay? Sometimes, like in this case, there is no plenum, there is no filter box, okay? So we have to do with what we have, and we have to install at the air return here. So it's not the ideal case because we are far away from the coil. So it will reduce a little bit the performance. It's not ideal case because you have to install much more nets than if you have the plenum and the filter box. So the cost for the client will be higher and the ROI will be a little bit bigger as well, okay? And sometimes when they do this, you can have the feeling that they don't do things in the right way always, And you must have, in general, around this hole and around this grill, some kind of plasterboard wall to guide and suck the air only from this grill to bring to the FCU, because otherwise you have a big area, okay, with a lot of air coming from multiple places, so it's not super efficient, but it works, and there's no other place where we can put continuum in this case, except buying a plenum and installing a plenum with continuum. That's a possibility. I don't know, depending on the country, the cost is different. Okay. So this is how it looks without plenum. So all these were real proof of concept with good results. You can see we put on the top of the filter and close. You can really see in transparency the fine coil and the filter. So that was a nice photo to explain. That was in a hotel in Bangkok. Okay, and that's it. Do you have any question?
No real question. Just to comment. Yeah, I was in Phuket a few days ago. Visited an hotel where it's exactly as you shown. I mean, the FCU is in a big space, and so part of the deal will be not only the net, but trying to. In fact, I feel more and more like an auditor when I arrive, auditing the aircon system and realizing that their compressors are on the roof under the sun, so that we could make it better by protecting them with small roofers, for example, that we could propose as a service, and the same for the FCU, which is in a large space above the ceiling, where it's not optimal, and seeing if we buy a plenum or if by ourselves we build a little box with medium or whatever material. So we see that more and more when we arrive, as you said, it's not only looking at the air, but looking at the whole environment and and how they, and most of the time, unfortunately, in all properties, it's not optimum.
It's a very good remark and really appreciate it, because the purpose of this training is not for all of us to become like super skilled and experts in air conditioning, but to have this in mind, because when we go everywhere with all the small things that I try to explain you today, you have a vision, global vision, and you can see how and where we can improve the performance. So we are becoming not only a continuum seller, okay? We are giving advice, doing some things to reduce globally the energy consumption. And sometimes, it comes with, we have to install or to propose together in the proposal plenum with a dust filter, or to close the area, because I have seen in some place with the FCU, like there is absolutely no enclosure on top of the ceiling between the slab and the ceiling, and they mix different rooms. When you are in a building, they mix the air from the next door room, okay? When you have no structural wall between two rooms, they suck the air from a room to another. So it doesn't make any sense, because sometimes you have the room next door that is not occupied, so the air is very hot. So you suck hot air that you cool to for the room where you have the person inside. So it's really not efficient. So just by closing the area and closing the air return to make sure that the air return is very well sealed and brings the air to the fine coil unit, makes it very efficient and improve the performance of continuum. So it's win-win for everybody. Any other question?
Not really. I will have to leave myself, Thomas. I'm sorry, but I have other commitment this morning.
It's already like 3 hours, and I guess Jenny has to
Yes.
to go to sleep as well. Thank you for your time.
Thomas,
Thank you for your time to explain everything, Thomas. I'm sure if we all have other questions, we can, you know,
You will
send
have the
them to
video and
you
the transcript, so you can have fun enjoying watching
as
again
well.
these 3 hours training again.
Yeah, and I think since we have some people, I was going to suggest to maybe have a continuum worldwide, like, I don't know, chat group or something,
Yeah.
if we have some insights or something to
What
share
I
with
will-
other
Yeah,
people.
this is what I intend to do, is to make, but in a different timeline where it's more
Yeah.
convenient for Europe and for you. So probably evening time for us here in Asia,
Mhm.
and morning time for you, and daytime for
Europe.
meeting, but like general, so everybody can. I will prepare an agenda. It's not a training. I will prepare an agenda with some topics, and I want to do it
Mhm.
monthly, so everybody can speak on the subject and exchange and win-win. And we do it monthly, and I would like it to be like mandatory for everyone, so we grow from our experience
Yep.
and we
I think
become
that's a
all
good
more
idea.
efficient. And some other training session like this
Yep.
at a different time. But yeah, I think it's important. And then after this meeting, make a like global group where we can chat and exchange. Yeah.
Yep.
Yeah.
Yes, Simon, you wanted to say something?
No, I was actually just going to make the same point, but and this is all recorded, right? And you'll send us a link to it all.
Exactly. With
Yeah.
the fantastic artificial intelligence tool that I'm a little bit scared because it's so powerful and so
Yeah.
efficient. It's incredible. It's like if I have a fantastic secretary doing all the things. Okay, thank you very
Yeah.
much. Have a wonderful Sunday.
Thank
Thank
you.
you.
Uh,
It was a pleasure meeting everyone.
meet you
And
today.
you, Jenny. Yeah. See you.
Bye.
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 Thank you. Thank you. Bye bye.
See you later, Mr. Thomas.
Thank you. Bye.